Besides the fact that every convergent sequence is bounded, somebody give me one more arrow that I can fill in this diagram. So the really big deal arrow is the one that goes from the southwest to the center on this one. Every Cauchy sequence is convergent. That's what I called in my write-up Theorem 3.3. So if I have a Cauchy sequence, that means that the terms of that sequence are getting arbitrarily close, not to some limit, but getting arbitrarily close to one another as we go out toward infinity. And it turns out that the real numbers have the property that every Cauchy sequence turns out to also have a limit. Not only every sequence of terms which gets closer and closer to itself will also get closer and closer to a limit, to use the backhanded calculus way of talking about convergence. So there's one more arrow, and that's probably the most conceptually gratifying one that we can fill in on this diagram for the real numbers. But the combination of monotonic and bounded guarantees convergence. And that theorem we call the monotone convergence theorem. So however you want to sort of depict this combination, that the two of those things together are enough to imply convergence. And we called that theorem 2.2 in my write-up, the monotone convergence theorem, or MCT. And the great thing about the monotone convergence theorem is that it's challenging to use the definition of convergence, but it's not as challenging to use the definitions of monotonicity and bounded. Those are two things that we can establish without having to do a lot of tricky, quantified logical arguments the way we have to do with convergence. So if I can prove that a given sequence is monotonic and that it's bounded, then I can deduce from the monotone convergence theorem that it's a convergent sequence. One more arrow we can fill in is that every convergent sequence is also a Cauchy sequence. That was in my write-up what I call Theorem 3.2. Every sequence which gets arbitrarily close to some limit also must get arbitrarily close to itself. And that's not just true for the real numbers. That's true actually in any metric space that we would want to show. It's this reverse arrow, Cauchy implies convergent, that we need the completeness property of the real numbers in order to justify. So I have that arrow as well. So one more arrow we can put in this diagram is just using the transitivity property of the logical implication. If A implies B and B implies C, then A must imply C. Every Cauchy sequence is convergent and every convergent sequence is bounded. That implies that every Cauchy sequence is bounded. And I actually provided a separate proof of that in the write-up as Theorem 3.1. So here are a lot of arrows that we can draw in this diagram. But equally interesting, I think, to the arrows that we can draw is the arrows that we cannot draw. So one of the first things I'd like for you all to think about in your groups today is what about the arrows that are not possible to draw on this diagram? So give me an example of one implication that is not, in fact, true. It's not true that just because a sequence is bounded means that it's convergent. And so what we might do is ask why not. If it's not true that Sn is bounded implies that Sn is convergent, give me a proof that that's not true. Sn is bounded does not imply Sn is convergent. What would a proof of that even look like? What do we need to do to establish that that logical implication is not a true statement? All we need to establish this claim is a counterexample. Because every logical implication is a universal claim, by construction. If I say that, for example, Sn is convergent implies Sn is bounded, that means for all convergent sequences, those sequences are bounded. And so if I want to negate one of those implications, I turn it from a for all into there exists. So to prove that Sn is bounded does not imply that Sn is convergent, I need to show that there exists what? There exists an Sn which is bounded and not convergent. So that's all that I need. I need a counterexample. Give me an example of a bounded sequence which is not convergent. What's an example? Negative 1 to the n. It's one of our favorite hobby horse sequences. Sn equals minus 1 to the n. This is a sequence which, why is it bounded, first of all? What is a bound for the entire, every term of the sequence? 1 and negative 1, although if we're using the definition of bounded, we just need not an n, sorry, we need a capital M. No, wait, sorry. We need, for all little n's, to be able to show that, whoops, I already screwed up this definition, that there exists a capital M, real number, such that for all little n's, it's true that the absolute value of Sn is less than or equal to m. So what capital M would work as a bound for this sequence? Two, as an example. Yeah, absolutely. So it's true that the absolute value of every term in this sequence is less than or equal to 2. Why? Because the absolute value of minus 1 to the n is equal to what? If I take the absolute value of a quantity which is always either positive or negative 1, what do I get? I get 1. Right, so that's why this inequality is in fact always a true statement for all n's. Right, is that for this sequence, the absolute value of every single term is 1. So minus 1 to the n is clearly a bounded sequence. But we already proved separately, quite some time ago now, when we were first thinking about the definition of convergence, minus 1 to the n was one of the sequences that we were using to wrap our heads around the definition. And at the time, we decided that we could negate the definition of convergence and show that minus 1 to the n satisfied the negative definition, in other words, the definition of not convergence, which would say that there exists an epsilon, so we picked here epsilon equals a half, such that any capital N that somebody were to choose, there exists some little n which is greater, for which the distance between that point in the sequence and the supposed limit, and here the supposed limit was 0, is greater than or equal to our epsilon. And that could always be the case no matter what capital N was chosen. We could find a little n for which it's further away from the limit than the epsilon that we chose. So we proved at the time that this sequence doesn't converge to 0. But we've also shown more recently that minus 1 to the n is not a Cauchy sequence. Because in fact, no matter how far out we go in the sequence, we can find 2 points in that sequence which are 2 units apart. So if we choose an epsilon that's smaller than 2, we can show that the sequence is also not a Cauchy sequence. And if we believe these 2 arrows, then that also means this is not a convergent sequence. So there's a counterexample for this one. So if we believe that convergent and Cauchy are in fact if and only if, and they are for the real numbers if we believe the results in this section, then not having an arrow from bounded to convergent also implies that we don't have an arrow from bounded to Cauchy. And we could in fact use the very same counterexample that we just did, right? Because minus 1 to the n is not a convergent sequence, that also means that it's not a Cauchy sequence. And yet it is a bounded sequence. So those 2 arrows we cannot draw. So I'm actually going to replace, when you said Cauchy, I'm going to replace with convergent just because it's a shorter arrow to draw. But because those 2 things are equivalent, it doesn't matter. So we're going to talk about the same thing. So monotonic does not imply convergent. Somebody give me a counterexample for that. So I'd be looking for an example of a sequence which was monotonic, but which is not convergent. So what's an example of a monotonic sequence which doesn't converge? One example of a sequence which is monotonic but which doesn't converge is this sequence, n squared over n. In fact, if we simplify that out, because n is always going to be a natural number, what is n squared over n better known as? N. So this is the sequence 1, 2, 3, 4, 5, 6, and so on and so on. Why is it a monotonic sequence? Yeah, it's true that every little n, every natural number, every index little n, satisfies that Sn is less than Sn plus 1. Why? Because Sn is equal to n, and Sn plus 1 is equal to n plus 1. And it's true that n is less than n plus 1 for all natural numbers n. So this is a strictly increasing, we would say, sequence of real numbers. And yet it's not a convergent sequence for a whole host of reasons. In fact, what does this sequence do that we have a definition for earlier in this chapter? Not only is it not convergent, what is it? Divergent to infinity. Right? No matter how high a ceiling we try to put on this sequence, there is an infinite tail of the sequence which is all above that ceiling. Right? Whatever ceiling we try to place on it, whatever capital M, there exists a little n such that all terms past that little nth term, capital Nth term, sorry, are above that ceiling, are greater than that capital M. So this is an example of a sequence which is, in fact, monotonic, but which is not convergent.